Everyone. Here we are going to start a new physical chemistry chapter, specific heat of solids. In the first lecture of this chapter, thermal expansion and isothermal compression, these two things will be discussed. So let's start with coefficient of thermal expansion, which is denoted as alpha. So alpha is the rate of increase in volume of a substance with respect to its increasing temperature at constant pressure per unit volume. So alpha. So this is del V by del Tp, that is the rate of change in volume with respect to temperature at constant pressure, and this rate of change in volume per unit volume, that is when it is multiplied by 1 by V, then it becomes the expression of alpha. So here this volume and volume, if cancel each other dimensionally, then only 1 by T, that is temperature inverse, remains as the dimension of alpha. So the dimension of alpha is temperature inverse, or symbolically it is theta inverse, and hence its unit is Kelvin inverse. Next comes thermal expansion of solids, because we know that there are three types of thermal expansion in case of solid substance: linear, areal, and volumetric. So they are denoted as alpha, beta, and gamma, and this is nothing but L2 minus L1 divided by T2 minus T1 divided by into 1 by L1. Here L1 is denoted as L0. So per unit length, the rate of change in length with respect to change in temperature is alpha, and the relative value, that is delta L by L0, is alpha delta T. Similarly, the areal expression is beta delta A by delta T into 1 by A0. A0 is the initial area, and hence the relative value delta A by A0 is beta into delta T. Similarly, volumetrically, gamma is delta V by delta T into 1 by V0, that is delta V by V0 equals to gamma into delta T. And here actually we are taking gamma. This is denoted as alpha in our main definition. So actually the volumetric expression, which will be denoted as alpha, will be taking into consideration. Next comes the point, coefficient of isothermal expansion. Since we have taken the term beta, so it should be denoted as beta T. Since it's isothermal, so T will be suffixed here. So what is the expression of beta T, or definition of beta T? Beta T is the rate of decrease in volume of a substance with respect to its increasing pressure at constant temperature per unit volume. So since according to Boyle's law, at constant temperature, pressure and volume are inversely proportional to each other, so a negative sign is here. And hence this rate of change in volume with respect to pressure at constant temperature per unit volume, that is into 1 by T, with a negative sign, is the expression of beta T. So dimensionally, volume cancelling each other, so 1 by pressure, that is pressure inverse, is the dimension of beta T, and hence its unit should be Pascal inverse. And if it's a solid substance, then final volume minus initial volume divided by final pressure minus initial pressure, and the expression should be like this: minus delta V by delta P into 1 by P, that is the relative value delta V by V must be equal to minus beta T into delta V, and this is all taking place at isothermal condition. Next, the expression of Cp minus Cv. We know in case of an ideal gas, Cp minus Cv equals to R, but in case of, what about in case of a real gas or a liquid or a solid? Then we can express this in terms of this alpha and beta T. We have the fundamental thermodynamic equation, delta du equals to Tds minus Pdv. Now, this volume, if kept constant, then this term would vanish, then it becomes isochorically du at constant volume must be equal to Tds at constant volume. Now, if we divide both sides by dt, then it looks like this. So since it is a partial condition, that is here in both, in this case, volume is kept constant, so this du is written as del u. So del u by del Tv, and here this ds becomes del s by del Tv by multiplying with dt. Now, we know this is actually Cv. Okay. So Cv has the expression in terms of entropy, which is equal to T into del S by del Tv. So we get the expression of heat capacity at constant volume as a function of entropy. Similarly, if we use the second fundamental equation of thermodynamics, that is dH equal to TdS plus VdP, in that case, by the same approach, almost same approach, we get the expression of Cp. Look, dH equals to TdS plus VdP. Here, the variable is pressure, so we have to keep the pressure constant. So isobarically, it becomes dH at constant pressure must be equal to TdS at constant pressure. Now, similarly, here, as likewise, the left hand side, in the right hand side also, we have to divide both sides by T. This way, this dH becomes del H by del Tp, and this one TdS becomes T into del S by del Tp. Since we know that this expression is nothing but the expression of heat capacity at constant pressure, so Cp is equal to T into del S by del Tp. So this is the expression of heat capacity at constant pressure in terms of entropy, and this is equation number 2. Now, let us express the total derivative of entropy as a function of temperature and volume. So if S is a function of T and V, then the total derivative ds must have the expression this one. This one does not need any more elaboration. We know all about this. Now we have to divide both sides by dt and impose the condition of constant pressure. So what would happen? This becomes del S del T P. Here dt would vanish, so this one will remain unchanged. But here, this one will be multiplied with del V del Tp. So, after having done this operation, this ds becomes del S del Tp, and this in the right hand side, this dt is vanished, and this one only is left unchanged, del S del Tv. And here, along with this one, a new thing is multiplied, del V del Tp. Now, you look in equation 1 and 2, we find that T into del S del Tp is Cp and T into del S del Tv is Cv. So, if we multiply both sides by temperature, then we get the expression of Cp and Cv in this equation. So, let us multiply both sides by T, and this way we get the expression in the left hand side, T into del S del Tv. This is nothing but Cp, and in the right hand side, in the first term, it is T into del S by del Tv. This is nothing but Cv, and the rest of this is, since temperature is coming, just joining them. So temperature, then this term, then this term. So we have the expression by putting the expression of T del S del Tp and T del S del Tv, that is Cp and Cv, in the above equation, then it becomes Cp equals to Cv plus T into del S del Vt into del V del Tp, or Cp minus Cv equals to this one. This is equation number 3. Now here the state functions t, v and p are observable, but here this part is not observable because this is entropy and this value is difficult to find out. So we have to convert this into express this in terms of pv or t. So this can be done with the help of Maxwell's relations, and with the help of Maxwell's relation, we can write, instead of del S del Vt, we can write del P del T V in this equation. So by putting in place of this one, if we put this one, then equation 3 becomes equation 4, and in equation 4 we have Cp minus Cv equals to T into del P del Tv and into del V del Tp. Here all only there are T, P and V and nothing else. So this is the expression of Cp minus Cv, and this is equation 4. And if you use the equation PV equal to nRT for an ideal gas, then easily you can prove that this one is nothing but R. Now, this one here is nothing but resembles with alpha, that is coefficient of thermal expansion, but this one does not resemble with anyone. So we have to eliminate this one with the help of expression of volume. So in order to do that, we have to take help of the cyclic rule. And if we apply the cyclic rule in case of with to P, V and T, then if we start with this one, then the cyclic rule is, we start with this one, del P del T V, T in the numerator, then T will goes to the denominator, V come add it to the numerator, then del V goes to the numerator, P goes to the denominator, and the constants here V, here P and here T, and the overall del P del T V, del T del V P, del V del Pt becomes minus 1. Or this one is equal to minus 1 divided by this 2. Look, this one becomes minus 1 divided by this one and this one. If we send this one into the numerator, then it would reciprocate. That means del T del Vp becomes del V del Tp. So this is nothing but equals to del V del Tp over this one, that is del V del Pt. So we have to put this value in equation number 4. Look, in equation number 4, we have this one, and the expression of this one, what we have got here? This one. So in place of del P del Tp, we have to put minus del B del Tp over del B del Pt. Okay. And this way we get equation number 5, like this. And definitely this negative sign would go here. So this is, and these two are, since are same, so they become squared. So minus T into del B del Tp whole squared divided by del B del Pt. Now we know the expressions of alpha and beta T. Alpha is del V del Tp 1 by V. That means this one is nothing but alpha V. And beta T is minus del V del Pt into 1 by V. That means this one is nothing but minus beta T into V. So just put here alpha V whole squared and put minus beta T into V. What we get? So this one we have said, this one is alpha V and this one is minus beta V. And putting this value, we get alpha V whole squared, and here in the denominator minus beta T into V. These negative signs would cancel each other. Then what would be left? The thing that would be left is nothing but equation number 7. So Cp minus Cv has the expression Tv alpha squared by beta T, which is a function of alpha and beta. So that's all for today's lecture. Thank you and have a nice day.